Hey folks, welcome to our final lesson in our unit on forces and momentum. In this lesson, we're going to be talking about Newton's second law of motion, which really is going to allow us to build on everything we've talked about so far and make that final connection between if there is a non-zero, unbalanced net force acting on an object, how will that affect its motion? So let's dive in. So just to review a couple key ideas that have brought us to this point so far. So first of all, what is net force? As a reminder, net force is the overall unbalanced, uncanceled out force that's acting on an object. So if we consider all the different forces, identify like what cancels out, subtract out anything that cancels out, and then anything that's left over that doesn't get canceled out, that describes our net force, the overall force acting on an object. Okay. Another question, if the net force on an object is zero, how will our object move? Well, if the net force is zero, then I know that my object is in equilibrium. And objects in equilibrium do not accelerate. They obey their own inertia, and so they maintain their constant velocity, which means that if an object is already sitting still and the net force is zero, it's going to keep sitting still. If an object is already moving along at some velocity and the net force is zero, it's going to keep moving along at that same velocity. Okay, so zero net force means zero acceleration, which means constant velocity. Okay. Last review question, if the net force on an object is not zero, how will the object move? So as we've been establishing here, forces cause acceleration. That's the whole goal of a force, is to change the motion of an object. And so if the net force is not zero, the motion is going to change, or in other words, our object will accelerate in the direction of that net force. Now, to figure out exactly how big that acceleration is, we come to Newton's second law. And this is what we discovered in our investigation previously, that we can see this relationship between net force and mass and acceleration that obeys this equation right here, that net force equals mass times acceleration. Okay, and so there are a couple different relationships that are kind of summed up in this. One is that net force and acceleration are linearly related to each other. So if I double the amount of force acting on an object, I'm going to double the acceleration as well. Another implied relationship in here is that for a given force, mass and acceleration are going to be inversely related to each other. So if I don't change the force, but I double the mass, the acceleration is going to drop in half. Okay, so we kind of have this like seesaw relationship between mass and acceleration. Okay, so all of that gets summed up in this equation here, that net force equals mass times acceleration. And so as long as I put my net force in newtons, my mass is measured in kilograms, and my acceleration is measured in meters per second squared, that equation will work for me. So we really want to be sure to be using those standard scientific units for this, because otherwise the conversions kind of end up messing with us. So we're going to stick with newtons, kilograms, and meters per second squared. So then what this means is net force, we have now established, can be calculated in two different ways. We can think of net force in two different ways. We can think of net force as the overall combined effect of all of our force vectors, right? And that's how we've thought about net force previously, is that net force is kind of the overall like leftover force after we've taken out everything that cancels out, okay? And that's still true. That's still a really good and important way to think about net force. But at the same time, now that we have Newton's second law, we can also think of net force as the product of mass and acceleration, that if we know the mass of the object and the rate at which it's accelerating, we multiply those together. That also tells us what the net force on the object has to be in order to be producing that acceleration. Okay, so two different ways of thinking of net force, and oftentimes we're going to need to think of net force in both of these ways. Okay, so net force is going to be our bridge between the individual forces acting on an object and the overall effect on motion, the acceleration of our object. So we really need to think of net force in both of these terms simultaneously to solve problems for this unit. Okay, so in terms of then solving problems, okay, if we have a situation where there is a non-zero net force acting on an object. Our forces don't all cancel, and so our object is accelerating. Here are some tips for how we can go about solving those problems. And what you're going to see is that we're really just kind of putting everything from this whole unit together here. Okay. First step is draw your free body diagram. Please do not resist me on this. It will help you. I promise. I swear. Okay. Draw that free body diagram. Draw all the forces that are acting on the object, just so you have a clear picture of what all is happening. So get in that gravitational force, normal force, tension force, applied force, friction force, any ones that apply, put them all in with their directions. Go ahead and label how big those forces are as well, if you are able to. Okay, so start with our free body diagram. That was the whole purpose of our first learning goal 2.1, was to draw that free body diagram, and so we're using it here. Second step is to use that free body diagram to write an equation for net force based on our individual forces. So that was the whole purpose of learning goal 2.2, was to take our free body diagram and figure out net force, and saying net force is equal to the upward force minus the downward force, or it's equal to the rightward force minus the leftward force. And sometimes we had to use Pythagorean theorem to put both of those together at the same time. Okay, but we're really going to need to keep doing that and keep thinking of our net force as sort of like the difference between any forces in opposite directions, any upward minus downward, or any rightward minus leftward. Okay, so that's your second step. Your third step is to write another equation for net force using Newton's second law. Okay, and again, net force is equal to mass times acceleration. So we're sort of using that equation as well. So at this point, we have two different equations for net force. One based on the individual forces in our free body diagram, one based on Newton's second law, that net force is equal to mass times acceleration. Another hint on this is to really be careful about direction, that if your acceleration is in the negative direction, so if your acceleration is going downward, or if it's going to the left, or maybe if our object is slowing down, depending on how we define things, we may want to make sure that our acceleration is negative, just to account for that and keep track of which direction our net force is in. Okay, so once we've done that, now we've got two equations for net force. We combine them together. We set those two equations for net force equal to each other and solve for whatever unknown value it is that we are solving for. All right, let's walk through an example of that, because I know that sounds kind of hand wavy. Okay, so let's walk through an example. All right, so say I've got a 10 kilogram box. I'm pushing it to the right across a surface that exerts 24.5 newtons of friction force on it. And as a result of my push and this friction force and all the forces that are acting on it, the box is accelerating to the right at 3 meters per second squared. So it's speeding up in the direction that I'm pushing it. Cool. So then the question is, how hard am I pushing in order to create that acceleration? Okay, so we see this is a situation where we're not in equilibrium, so I know my forces aren't balancing out. I've got some sort of non-zero net force. And so then I'm going to go ahead and follow these 4 steps to really figure out, like, okay, what is going on here, to relate the motion to the individual forces acting on this box. Okay, so first step is to draw my free body diagram. So here's the box. All right, yay. And so then from there, I'm going to start including all the different forces acting on it. So again, this is learning goal 2.1, identifying those types of forces and drawing our free body diagrams. Okay, so I identify ultimately 4 different forces that are acting upon this box. I see an applied force directed to the right, because I'm pushing the box to the right, okay? And then there's also a friction force acting on it. Now, if the box is getting pushed to the right, it's moving to the right, it's accelerating to the right, then I expect that the friction force is moving against that motion, right? So if the box is moving to the right, the friction force is pushing it to the left, trying to thwart that motion, all right? So I've got both of those. I also always have a gravitational force that is acting upon the box. There it is right there. I can even calculate that gravitational force using my equation weight equals mass times gravitational acceleration. Assuming that this box is here on Earth, that gravitational acceleration is 9.8 meters per second squared. So I'll just multiply that by the mass of 10 kilograms to get a gravitational force of 98 newtons downward, all right? And then we've got this downward force, but hopefully our box isn't like plummeting downward. It is in fact staying on the surface, which means that this gravitational force must be getting canceled out by a normal force upward. So if gravity is pulling the box down with 98 newtons of force, the floor is also pushing up with 98 newtons of force to cancel out that weight, to balance it out so that we don't have our box falling down through the floor. Right? So those are all the forces I see acting on it. No tension force because there's nothing pulling on the box, nothing like that. But all the other forces, I believe, are in play here. Okay, so there's my free body diagram. My next step then is to use this free body diagram to write out an equation for net force. And I've got two different dimensions in play here. And so I want to think about each of those separately. I want to think about my vertical dimension and I want to think about my horizontal dimension. Okay, so if I look at this, I should immediately see that in one dimension, my forces cancel out. Specifically in my vertical dimension, normal force minus gravitational force, that's just zero, okay? They already cancel out, so they're not contributing anything to the acceleration of the box. They're not contributing to the net force. However, in the horizontal direction, I don't have everything necessarily canceling out. What I see here is that I've got an applied force directed to the right and a friction force directed to the left. And so the way that I would figure out the net force based on those two forces is by simply subtracting them, right? Because they're in opposite directions from each other. And so the net force is whatever the difference is between those two. So applied force minus friction force gives me the overall net force acting on the object. And I happen to know that the friction force is 24.5 newtons, so I can go ahead and just plug that right in now. But I don't currently know what the net force is, and I don't currently know what the applied force is. So this equation isn't enough to allow me to solve because I have two unknowns in here, and I need to have just one unknown in order to be able to solve it algebraically, okay? The good news is this is where Newton's second law comes into play. So our next step is to write another equation for net force based on Newton's second law, right? So Newton's second law says that net force equals mass times acceleration. Well, I know that the mass of this box is 10 kilograms. I know that's the mass because it's in kilograms and mass is in kilograms, all right? So it's 10 kilograms in mass, and then it also says that the box is accelerating to the right at 3 meters per second squared. So acceleration equals 3 meters per second squared. I'll go ahead and leave that as positive because it's to the right, and I generally think of right as being positive and up as being positive and so on and so forth, all right? So acceleration is 3 meters per second squared. And so if I want to find net force, all I have to do is multiply those two together. So 10 kilograms times 3 meters per second squared gives me an overall net force of 30 newtons to the right in what I would consider the positive direction. Okay, so overall I've got 30 more newtons going to the right than I do to the left. And that's what's causing this acceleration. Okay. So now I've written two different equations for net force, one based on my free body diagram where I said, okay, it's equal to the difference in my forces, my right force minus my left force. And I've written an equation for net force based on Newton's second law, that net force is equal to mass times acceleration. Right? So my last step then is just to combine those two equations together, okay? So I've written from my free body diagram that net force equals applied force minus that friction force because they're in opposite directions, so the net force is the difference between them. And I've written that my net force is equal to 30 newtons, and I got that using Newton's second law, that mass times acceleration gives me 30 newtons of net force. So now all I have to do is just combine those two equations together, set them equal to each other. Which gives me 30 newtons, the net force, is equal to the applied force minus that 24.5 newtons of friction force. And so then all I have to do to solve for applied force is add 24.5 to both sides. And that gives me an overall applied force of 54.5 newtons, okay? Because my applied force has to be 30 newtons bigger than the friction force for us to have 30 newtons of net force. And we have to have 30 newtons of net force in order to produce an acceleration of 3 meters per second squared to the right. Right? So that is the overview of how we're using net force and Newton's second law to solve these problems. Okay, so the general idea of F net equals ma, that's pretty quick and simple, that's fine. That's an easy equation for us to grab onto. But the hard part with this is really going to be practicing using and putting all of these things together. So I encourage you to go try out some practice problems, put this into use, and let me know what questions you run into along the way. Thank you so much for watching.